Hi everybody, in this video we are still on the 5.1, so this page is the very first page in the packet, 5.1, but we are on the bottom where it says Pascal's triangle. This is a really cool, it's one of my favorite parts of Algebra 2. I just think that things like this are really cool. Why do I think it's so cool? Well, part of it is because there's history involved, and I just think that history is interesting. Also, patterns. Like, that's the whole reason we study math, right? It's because of patterns. And Pascal's triangle has a gazillion patterns in it, which is super cool. So first of all, it's called Pascal's triangle. A little bit of history. You do not have to write all this down, so don't worry about writing this down. But interesting history. Pascal, all the way down here in 1623, was Pascal's time, and that's when he was studying this triangle. He wrote the treatise on the arithmetical triangle in 1655. It was in French, so this is the English translation, because Blaise himself was French. So it's called Pascal's triangle here in the US. That's what we call it. But you know what? They don't call it Pascal's triangle everywhere, because actually it predates Pascal by hundreds of years. In the 11th century, the Chinese and the Persians, which are the Iraq and current modern-day Iraq, were studying this triangle. A guy named, and I don't know how to pronounce this, Shen, maybe, in 1050 used it to solve squares and cubics. And another guy named Yang used it for the binomial coefficients. So in China, they actually call it the Yang triangle. They don't call it the Pascal triangle, they call it Yang triangle. And both of these things, solving squares and cubics and using for binomial coefficients, those are two of the main things that we are going to use it for. And then Pascal came along 500 years later and said, hey, there's this really cool triangle. And I figured it out. But he didn't figure it out, but he put it all together in a treatise. He wrote about it, so that way other mathematicians could read about it and then learn from it. So that's a little bit of history. I just think it's super cool. I want you to look at this triangle and look and find some patterns. There are a lot of patterns. Pause the video, try to come up with some patterns, and then, with those patterns, can you fill in the next two rows? See if you're able to do that. Pause it here, see what you come up with. All right, welcome back. Here are the row 6 and row 7. I should talk a little bit about the row numbers. This is row 0, but yet it has a row. Row 1 just has a bunch of 1s in it. Row 2, it looks like it's the third row, but we call it row 2. And the way I remember it is because row 3 has a bunch of 3s in it, and row 4 has a bunch of 4s in it, etc., etc. That's how I remember the row numbers. I don't refer to row numbers a lot. I mostly just use it, and we'll talk about that too. So that's how it's set up. Now, what were some of the patterns? I'm going to have you in class. I'm going to have you show me what some of your patterns were, because like I said, there are a bunch. But for what we want to know for what we're doing in this unit is the pattern that I'm looking at is I add these two together and they add up to 4. And I add 4 and 6 together and they add up to 10. And so if I go down here, well, another obvious pattern hopefully everyone saw was that they go 1 all the way down here, right? 1's all the way down. And then 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. But what I'm looking for is how do I make the inner parts of it, not just the 1s, but the rest of it. So 1 plus 5 is 6. 5 plus 10 is 15. 10 and 10 is 20, etc., 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 etc. And so you should be able to reproduce this triangle. Like if you're in the middle of a quiz, you might have to quickly do it. I'm not having a quiz on the triangle, but it's one of those things that when you're in the middle of a test, or maybe when you get your test, you write it down real quick because you need to know all this. Okay, 1 plus 6 is 7, 6 plus 15 is 21, 15 plus 20 is 35, etc., etc., etc. Now, in this class, we won't really get to row 7 very much, but row 3, 4, and 5, we will do quite a bit of that, even maybe row 6 here and there, okay? So we need to understand how it's built, and this is how it's built. Let's turn the page. So remember I said when you get a quiz or a test or whatever, you're doing your homework, you might want to write it out. And I'm going to do that right now because it is something that I need to know, or at least have access to. I don't have it memorized. I don't. If you said, what's the 8th row? I have no idea what the 8th row is. What I have to do is I have to rewrite it every time. So that's fine. I'm going to rewrite it, and I'm probably going to stop here at the 5th row. because I know I won't need to go much higher than that. Okay, so there I have it in case I need it. All right, changing topics slightly, but not too much. You know how to do exponents. We talked about that before. Anything to the 0 power is what? Anything to the 0 power is 1. So I'm going to put a 1 here. Okay, anything to the first power is just itself. So I have an x and a y. Now, second power, I need to do that, which we memorized a rule, and you might have that memorized, or you might have to work it out. I don't care which way you do it. Whichever way you do it, we come up with x squared plus 2xy plus y squared. So I'm going to write that in this next line. X squared plus 2xy plus y squared. Now, third power. Holy cow, how am I going to do that? Well, what I have to do is I have to take this that I already had, and I have to multiply it by x plus y. And now I have to multiply this all out. It's going to take a while. Pause the video here, multiply it out, and we'll come back and check. Okay, so I multiplied it out. I got all these little terms in here. I added my like terms, and when I added my like terms, I got x to the third plus 3x squared y plus 3xy squared plus, that should be a third, y to the third. What does that have to do with Pascal's triangle? Well, let's take a look. Look at the numbers that are here. And I didn't write my 1's here, but I could have. That's a 1x and a 1y and a 1x squared and a 1y squared, etc., etc. Okay, look at those numbers. I have a 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. It's following Pascal's triangle. It's the same exact numbers. Now we also have some other things. We have some x's and we have some y's and blah, blah, blah. But the numbers themselves are following Pascal's triangle pattern. And so I can predict accurately that I don't have to multiply that out again to get the next one. Holy cow, that would take forever, right? I don't have to do it. What I can do is I can look at my next line here. And this is a fourth power, so I'm going to go to my fourth line, and I'm going to give myself some space and space out like this triangle. And I'm going to go 1, 4, 6, 4, 1. Okay, now we haven't talked about the x's and y's yet, but the coefficients are going to be 1, 4, 6, 4, 1 because that's what Pascal's triangle has. That's the next line in the row, and the next row in the triangle. Now, what else? What about the x's and the y's? Well, let's take a look. How about the x's? Let's just take a look at the first term. So I'm talking about going down here and just looking at those x's. That didn't have an x. That has x to the first, x to the second, x to the third. Can you guess what's going to be here? Of course you can. That's going to be x to the fourth, right? And that's true. And then a plus. Let's go down the other way. Like with the y's, right? Same pattern, but just y's. So 0, 1, 2, 3. This last one, which I gave myself a lot of space because I might need that space. That's going to be y to the fourth, isn't it? Okay, that's kind of obvious, I hope. We can see that. Now, the next term is not as obvious, but actually it's going to follow another pattern. So look at how there's no x, but there's a y. And then there's an x and a y. And then an x squared and a y. And so every time there's just a y, right? But then the x is getting more and more powers on the x. So here was x to the second. So next time now it's going to be x to the third. 4x to the third. And plus that y is stuck on there on the end. It's a times. I said the word plus, but that means also. So a y added on, multiplied on the end. Let's look at the next one. This one has a y squared and then a y squared. Well, I bet this has a y squared. What about the x's? Well, similar thing as before, but we're just starting one off. So no x, x. Don't you think it's going to be x to the second? Okay. And then the next term, I'm going to look at it this way. I'm going to look at it this way. Okay, that's going to fill in these spaces here. So Look, this time the x stays consistent. It's x, 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 and then the y goes up. So this is an x and then a y to the third. Okay, and then I'm done. So if I know what patterns to look for in my triangle, I don't have to do all this. I can, but man, it takes a while. I can instead look for some patterns. Okay, I want you to pause the video here and see what you can do on this text box down here of what are some of the patterns. Can you find some of the patterns and fill in those blanks? All right, I want to talk about this. And we'll talk about it more in class, but I want to go through it real quickly. How many terms it has, like this has a first term, just one term. This has two terms. This has three terms. So x to the first has two terms. X to the second has three terms. X to the third has four terms. So I call that n plus 1. Whatever the n is, and then one more is going to be how many terms there are. Okay, the exponents. Now this time I had been like going down the triangle, and this is getting awfully messy, and so I wish I didn't have such a mess, but here we are. Let's talk about how about what's going on like on a line instead of down the diagonals, right? Just like in a single row, what's happening? Okay, in a single row, my exponents, I have x to the fourth, and then x to the third, x to the second. Do you see it's going down one every time? X to the first, no x. So it starts at x to the n, because n is 4. Starts at x to the n, goes down, 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 no x. The y's go the other way. I have y to the fourth, because that's what the power is, and then y to the third, y to the second, y, and no y. So it starts at y to the 0, and it goes up to y to the fourth, or from right to left, it goes the other way. The first term always starts with a 1, right? And it's always 1x to the n. So if this is the fourth, n is 4, it's 1x to the fourth. If n is 3, it's 1x to the third. So whatever then. Now then the last term is always 1y to the whatever. Okay. The second term, remember how like this is the third row because there's a bunch of 3s. This is the fourth row because there's a bunch of 4s. The first term is just x to the n. The second term is whatever that n number is, goes in front, and the next one down, and then a y. And so that's a little bit confusing, but you might catch on to that a little bit more. The coefficient of the second term is always n. That's kind of the main thing I want to talk about there. Now, the sum of the exponents is quite handy. It's one that I use to kind of check myself. The sum of the exponents is n. What I mean is this is a fourth power, right? Okay, so here's an exponent of 4. Here's a 3 and a 1, that's 4. A 2 and a 2, that's 4. A 1 and a 3, 4. A 4. So we can always add up those exponents on the x's and y's, and they add up to n. Remember on the other side, I said that they were starting to use these to solve squares and cubics in 1050. And Yang Hui in 1261 through 1275 was coming up with the binomial coefficients. That's what we're doing right now. We're doing the binomial coefficients. And so we're going to be using the coefficients and how does this binomial, how can I multiply it out without actually multiplying it out? What is the pattern? And that's the patterns we've been talking about. Okay, so first of all, consider a couple of different things. I'm just going to reproduce up here so that I have it. And this one is a third power, so I really only am going to be referring to this line. And I have to look at all these rules that I just, like patterns I just noticed and see how to put those together. I'm going to start with just writing out my coefficients. I have a 1, a 3, and a 1. I'm giving myself some space to write things in there. In this case, I don't have a y anymore, do I? I have an x, which is x, but my y is actually 5. So again, my calculator is going to come into play here, okay? So my 1, and then my first term is always x to whatever power it is, x to the third. Now, I like to sometimes just go down from the x's. So 1x to the third, and then 3x squared, and 3x, and oops, no x on that last one. Okay, how about the y's? Well, The y's start off at 0. That's what this one is. Y starts off y to the 0. That's why I did not have a y here. But then the next one goes up. And so the y is going to go no y here, but then a y to the first here, a y to the second here, and a y to the third here. But oh no, I don't have y, I have 5, darn it. So I have to put in a 5 instead. So I have 1x to the third, that one's done, there's no 5. This one has a 3x squared times 5 to the first. This one has a 3x times 5 squared, and this has a 1 times 5 to the third. I just plugged in a 5. Everywhere I had a y, I plugged in a 5. You might need your calculator now. So I'm going to have 1x to the third plus, oops, I wrote 25. It's supposed to be 15. So 15, because 5 times 3 is 15, x squared. Here I have 25 times 3, that's 75x. And here I have 5 times 5 times 5, which is 125. So there is my final answer for what is x plus 5 to the third power. I could have multiplied it all out, like I did up here on the margin, but that really took a long time, and I thought there's got to be a better way. And thanks to Blaise Pascal and, I don't remember his name, I have to come back and find his name, Yang Wei, I now know that there's a shorter way to do it, and I don't have to multiply them all out. I can just come up with my patterns, and there I have my answer. Okay, we will be doing a lot more of this in class, and so I'm going to save these next two examples for class.